Today we are talking about the fundamental counting principle, which I refer to as the FCP. Rolls off the tongue a lot nicer. Also, when you get introduced to more problem types as we go from each set of notes to the next, you're going to be able to need to identify these specific problems as FCP, so you're going to need to get used to it by its name. Before we get started, a couple of vocab words to take a look at. These are going to appear in the notes a few different times, like a few different notes from these notes. So it's good to just have a basic introduction to what they are and what they mean. Sample space and sample size. A lot of students mix these up. Sample space is the set or list of possible outcomes of an experiment. So what are the possible options you can get when you do an experiment? Not how many. How many, the number of options, that's sample size. We'll look at a couple examples of these so you really get to know the difference between the two. And it's important that you're answering the question that's being asked with those. Let's take a look at an example of that. Create the sample space for the following problem. You go to the snack bar to buy a bagel and a drink for lunch. You can choose from a plain bagel, a blueberry bagel, or a raisin bagel. The choices for a drink include water or a sports drink. List the different lunches that could be made with these choices, all of your possible lunch combinations. So this is going to involve quite a bit of writing. None of the other problems will be this extensive. Let's start with our bagel options. First bagel option is the plain bagel. And I'll be writing that out again when I do it next time. It'll just be a P. Blueberry bagel. And I'm going to use BB for short. And the raisin bagel. And I'll use an R for that. So we'll choose a bagel and we'll choose a drink. 2 drinks, water, or a sports drink. So we're seeing how many lunches we can make if we choose one from each category. Again, we'll go through all possible combinations. So we're going to list our lunch combos. When we do that, I'm going to number them so I can keep track of how many I have as I go. When you go through choosing these, so to make sure you get all of your combinations written down, you want to do this in a systematic way. So we'll start with the top of each list. We'll go with a plain bagel and a water. Then we'll go with the plain bagel and a sports drink. And then we'll go through all the bagels in that manner. So first option, we have a plain bagel, so P, bagel, plus water. It's our first lunch option. Second lunch option, we can do the plain bagel, but with a sports drink. And we'll do that again, but with a blueberry bagel. Let's say we want a blueberry, BB, bagel with a water, or a blueberry bagel with a sports drink. Lastly, we can do that with the raisin bagel, the R bagel. A raisin bagel with a water, or a raisin bagel with a sports drink. Those are all the possible lunches you can make from this menu. Now this here is called the sample space. I have written out in plain words what my options are. The question below, what is the sample size of the lunch options? That's how many lunches I can make. We got 6. 6 lunch options. So understand the difference between sample size and sample space. Sample space, you write out the actual options you have to choose from in words. Sample size is how many options you have to pick from. This is the long way of doing these problems. There is a shortcut, and that is what the fundamental counting principle, FCP, states. If one event or experiment can occur in M as in mower, ways, and another event, experiment, can occur in N as in noodle, ways, then the number of ways the 2 events can occur is M times N. So let's look at this problem again now that we know the shortcut. We had 3 bagel options and 2 drink options. So we could have just done 3 times 2, and we know that we should get 6 possible combinations, the 6 that we already listed out. That is the shortcut for these problems. Questions on sample space, sample size? Now that we know what the FCP says, we can use it to our advantage. Use the fundamental counting principle to find the total number of outcomes in each situation. Just a heads up reminder, these are notes, so I am going to go a little bit more detailed than I'm sure most of you will when you do a problem like this. That's fine, although writing it out the way I do, I think wouldn't be a bad idea. That's just me. Number 1. Choosing from 8 car models, 5 exterior paint colors, and 2 interior colors. I'm going to write those out. Those are categories. So we have car models. And I'm just going to say exterior colors for short. This is really just for organization, so you can abbreviate however you want. Interior colors is going to be my last category. In the future, you'll come to realize that you'll have an FCP problem if you can make categories of things. That's a dead giveaway. 8 car models, and we have 8 choices. You can also call them outcomes. Outcomes works for every single problem. For exterior colors, we have 5 choices. And then for interior, we only have 2 choices. We can use the FCP to quickly get the overall number of choices or outcomes. You take those 3 numbers and you multiply them. 8 times 5 times 2. And that's 80 outcomes. 80 outcomes, 80 choices, 80 cars, whatever you want to say there. Outcomes will always work though. Now let's talk about showing work for a moment. I imagine most of you will show me this on a homework test or quiz. This is fine. What I don't want to see is this. Couple reasons why. First off, especially on a test, I don't know if this came from your head, your calculator, or the paper next to you. So I need to see some work. There's another big reason why, and it's for your benefit. If you put the answer down on a 2-point problem and it's wrong, how many points are you losing?
Wait,
2 points. If it's a 2-point, it's okay. If you use a 2-point problem and you put down a wrong answer, it's right or wrong. I can't go halvesies. I have no idea how you got that number. If you show me your work, depending on how close it is, I can give a point. And this happens all the time. I have students write the correct work and the wrong answer because of a calculator error. That is definitely a reason to show your work. It sucks when you have the right work and you get the wrong answer. But if you show the work, I can still give some credit. And this test especially, it's going to be very quick calculations like this. So if you don't show your work, you're going to lose a lot of points. So there's my spiel. At the very least, show me what you're doing to get that number, please. Number 2. Rolling 2 number cubes, in other words, a pair of dice. 6-sided dice, the standard ones. 2 cubes here. Cube number 1. Cube number 2. This one seems a bit obvious, but I strongly recommend you write them out because I see these get messed up all the time. Cube 1, there are 6 outcomes. And cube 2, there are also 6 outcomes. Multiply them, not add them. 6 times 6. 36 outcomes when we roll a pair of dice. Didn't mean to box that whole thing, just the 36. That's okay. Number 3, put a star next to it. This problem is very easy, and it's very easy to mess up. It's actually, some of my best students are going to miss this problem because we're overthinking, or we're not thinking hard enough. I'm not sure which one it is. But we've got 3 coins. This is why I recommend you show work so you avoid a very easy mistake. We have coin number 1, coin number 2, and coin number 3. I can give you any coin from any currency system. How many sides does it have? 2. So each of these has 2 outcomes. I'm going to get specific here just because you'll need this information for the homework. What do we call those 2 outcomes? They have names.
Heads and tails.
Heads and tails, thank you. No. There's just a lot of vocab and a lot of labeling in this unit, so I really push it in the notes. But no, I'm more focused on if the numbers are right on a test or a quiz. Here's the big mistake that people do. There are 3 coins, 2 outcomes each, so they'll do 2 times 3 and get 6. It's 2 times itself 3 times. 2 times 2 times 2, which is 8. So do not make that mistake. I've already seen it a couple times today. 2 times 2 times 2, not 2 times 3. Different things. 8 outcomes. Questions on these first 3 before we go on to the back? Number 5. The math club is electing new officers. There are 3 candidates for president, 4 candidates for vice president, 4 candidates for secretary, and 2 candidates for treasurer. How many different combinations of officers are possible? Again, I'm going to make an organized list to start. So we have president, I'm going to go pres for short, VP for vice president, SEC for secretary, and trez for treasurer. Here's a pro tip. When you skim back through the problem to pull those numbers out and write them down, it can be very easy to grab the wrong number. So I'm going to do this. Just takes a moment just so I don't grab the wrong number for the wrong thing. So it's 3 candidates for president. Vice president is 4. Secretary also gets 4. And then treasurer gets 2. That way I connect them visually speaking. I won't grab the wrong number when I'm filling them in. When you get into a paragraph long word problems, again, it can be very easy to make a mistake. President has three outcomes, choices, options, whatever you want to put there. VP has 4 outcomes. 4 for secretary. And 2 for treasurer. And then we multiply all those together. 3 times 4 times 4 times 2. That gives us a grand total of 96 outcomes. This election can go 96 different ways. Questions on number 5. Number 6. Find the number of outcomes when a coin is tossed, heads or tails, and an ace is drawn from the 4 possible aces in a deck of cards. Just these 4 here. Hopefully you've had a lot of experience with the deck of cards. If not, there are 4 suits: spade, diamond, club, heart. They are in the order that they are in the picture, from left to right. When we draw the card, we're drawing it from these 4. We're not taking a deck of cards and then pulling an ace out of it. That distinction is very important here. So we're looking at essentially what we're testing. So we have a coin, which we discussed earlier, has 2 outcomes. And again, we're picking from just these 4 cards. So there's 4 outcomes. And we multiply. 2 times 4. So we have 8 outcomes. Questions before I do the password problems? Last 2 password problems. I love these. They require you to think just a little bit more about what you're going to put down. So make sure you take your time on these. Determine how many different computer passwords are possible if. I'm going to start by reading the problem, and then we're going to dig into the terms a little bit more before I create the answer. 3 digits followed by 4 letters repeats aloud. Let's talk about digits and letters. There are standard amounts you need to be aware of for these, if not already. Letters, your options are obviously the alphabet, A through Z. How many letters are there on the alphabet?
4.
Nope, higher.
27.
Lower, Harneet. 26, thank you.
Algebra. Good numbers now.
So, if you didn't know, there are 26 letters in the alphabet. If you don't know that on the test or quiz, write them out. Count them. 26. 26 options. Let's talk about digits because that one comes up a lot. When we say digits, we're referring to a singular number. So, not 25, not 300. Singular digits. How many are there?
9.
No.
What?
A lot. That's why I put it out there. A lot of students think there's 9. There are 10. Day. 1 through 9 plus what other digit?
0.
0. That's what we forget about because we start with 1 and then when we get to 10 we're like, oh, 10's 2 digits. But 0 is still a singular digit. So I'm going to list them out just this once. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. See that there are 10 digits there. 10 total to choose from. So we have 10 options. Again, I put it out there. It comes up a lot, and a lot of students think it's 9. So I want to clear the air now. It's actually 10. Now that we've got that essential information down, let's go do number 7. We want to create a computer password that has 3 digits followed by 4 letters. That's our criteria. So let's create a template for this password like we're trying to fill it in. I'm going to make 7 blanks. We're not going to do that, but that is a way to think about it. So the first 3 blanks must have a digit, so I'm going to put a D under the first 3. The next 4 have to be a letter, so I'm going to put L's under those. Now this criteria is important. Repeats are allowed, so I can reuse the same number or the same digit as many times as I want. That's important. So when I pick out my first digit, I have 10 options to choose from. So I could put 10 different things in this blank. Again, we're trying to figure out how many possible passwords I can make. So we need to think about all options. The next blank, I'm allowed to reuse the same digit if I want. So I still have 10 options to choose from for the second blank. And again for the third. I could put the same number in all 3 blanks if I wanted to. Probably not the smartest decision, but you could do it. Letters, same thing, but we have 26 options. And we could repeat for all 4 blanks if we wanted to. So we have the same 26 options for all 4 blanks. This is where you're really going to need a calculator. Remember, we are multiplying all of these together. 10 times 10 times 10 times 26 times 26 times 26 times 26. Let's take a moment and do that. Carefully, it's very easy to make a typo here. What's a lot to remember? Fair. Just remember you're multiplying. And I made a mistake already. No, I didn't. Let me check on it. Nope. I just thought it was a different number. Let me write that down before I read it. We have 4, 5, 6, 9, 7, 6, 0, 0, 0. If you were going to put commas in there, every 3 numbers gets a comma. So I got these 3 zeros, comma, these 3, comma, and then I can't put any more in. If you're worried you're going to mess the commas up, don't put them in your answer. Just write the numbers and we're going to be good. This is 456,976,000 passwords. For number 8, we have the same criteria except no repeats allowed. Let's see how that changes our number. The other criteria is exactly the same, 3 digits, 4 letters. So I'm going to set up the same template, 7 blanks. First 3 are digits. Back 3 or back 4 are letters. This time it matters the order I go in. So we start with that first blank of digits. I get first choice. I have 10 digits to choose from. Whatever number I put in the first digit cannot be used in the second one. So what am I going to write in this blank? 9, exactly. I take a choice away each time since repeats are not allowed. So the next place, I now have 2 I can't choose because they were used for the first 2 blanks. We do the same thing with letters. First letter, I have all the options. I got 26 of them. When I use one, I take it away. Now I have 25 left for the second blank, 24, 23. And again, we multiply all of those together. Bless you. Oh. We'll multiply that in our calculators to get the new number. this is what it came out with. 258336000. Again, every 3 numbers gets a comma if you choose to use the commas. That's how they work. 258,336,000 passwords, which is still a lot, but it's almost half as many as the first number I got, number 7. So that's a significant difference. Questions on the password problems?